local heroes. This week I'm commemorating the 100th anniversary of the Nobel Prize Foundation. So all my heroes won Nobel Prizes, except one. He was a brilliant inventor and took out 350 patents in his lifetime. He was also a great entrepreneur and founded an industrial empire that stretched around the world and was worth millions of pounds. His two most famous inventions were dynamite and the Nobel Prizes, and his name was Alfred Nobel. Alfred Nobel was born in Stockholm, Sweden, but spent his teenage years in Russia. By the age of 17, he was fluent in Swedish, Russian, French, German and English. I've come to the Ardeer Peninsula in Ayrshire, south of Glasgow, where in 1871 Nobel built his only British factory. But his story starts much earlier, when he was still a teenager. On a trip to Paris, he met a young Italian scientist called Ascanio Sobrero, who had just treated glycerin or glycerol with acids to make this stuff, nitroglycerin. Now this is a very powerful explosive, but the trouble is it goes off very easily. Just watch what happens when I take a little drop on this piece of paper and put it down on this slab, like that. And then I'll just get rid of the rest of this, and you'll see it's got a rubber bung, no screw top. You do not want any friction with this stuff. Now just watch what happens when I hit that with a hammer. 1, 2, 3. Wow. So you see, you would not want to transport a ton of that across country on the back of a lorry, because one little pothole and the whole lot might go up. However, Alfred saw the potential in it, and he and his father went back to Stockholm and set up a small laboratory. Then in 1864, disaster struck. The lab blew up and Alfred's younger brother Emil was killed. Clearly, the nitroglycerin had to be tamed. Well, it took Alfred 3 years, and finally he did it using this. This stuff is called kieselguhr, and it's a special sort of clay which dried out, is very much like talc and very absorbent. And so what he did was to mix 3 parts of nitroglycerin with 1 part of kieselguhr, and he came up with this, and this was dynamite. The great thing about dynamite is it was much easier to handle, so they could make sticks of it, and then it was much more practical to take this stuff around. Just look, I ought to be able to drop this and come to no harm. And it won't go off. Fantastic, isn't it? Now, I want to see what a stick of dynamite will do. And because this stuff is rather easy to handle and difficult to set off, I'm going to use another of Nobel's inventions. This, the blasting cap. This is a detonator, and that's on the end of an ordinary bit of safety fuse, and I'm going to put it into a hole I've already made in my dynamite. Then I'm going to set the stick on this thick plastic witness plate here, and we'll see what effect the explosion has on it. Before they could make their dynamite, they had to make the nitroglycerin, and that was fantastically dangerous. First of all, the mixture with which they made it must not get too hot, so they employed a man just to look at the temperature of the mixture. And to make sure he didn't fall asleep, they sat him on a one-legged stool so that he'd fall over and wake up again. But secondly, they couldn't pump the nitroglycerin because it was so sensitive, so they used to make it on top of this hill, which was actually called Nitroglycerin Hill. And when it had been made, it trickled down by gravity, no pumping, to this wash house where it was washed clean. And then the purified nitroglycerin would trickle further down to a whole series of mixing sheds beyond where this one is now. That's where it was mixed with kieselguhr, and that's how they made their dynamite. In the factory, people were very careful about nitroglycerin because they knew the dangers. But the people working around got to be rather too familiar with it. And the miners would use nitro to lubricate the wheels of their wagons. And what's more, they were a bit fed up with the candles they carried for lights in their hats, and so they replaced them with little lamps, and they burnt nitroglycerin because it burnt with a lovely bright flame. The most surprising thing about Nobel was his will. He left most of his vast fortune in a trust that was to award prizes to those who had conferred the greatest benefit on mankind in the fields of physics,
chemistry, physiology, literature and peace.
Alfred's will was contested by some of the family and also by some of his fellow countrymen, who objected to prize money being given to non-Swedes. Nevertheless, in 1900, the foundation was set up, and in the following year they began to give away the prizes that have become the greatest legacy of Alfred Nobel.
I was really surprised when I discovered that one of the country's leading places for research into tropical medicine was right here in Liverpool. Liverpool certainly doesn't feel very tropical, but the fact is that at the turn of the century the British Empire spanned the globe, and hundreds of people came here from all over the tropics, and with them came all sorts of horrid tropical diseases.
My next hero solved a problem that had plagued humanity for centuries. He worked out how malaria is spread. And for that work, he was awarded the first ever British Nobel Prize in any subject. His name was Ronald Ross.
Ronald Ross was born in a military outpost at Almora in the Himalayas, where his father was serving as an army captain. At the age of 8, he was shipped back to England, where he was passed between relatives and boarding schools. He ended up studying medicine and joined the Indian Medical Service.
Malaria was a big killer in India, but no one knew very much about it. In the early days, they put down the cause to the rotten air over the swamps. Malaria meant bad air. But what they did know was that the blood of infected patients always had a whole lot of little black blobs in it. And they thought these might have something to do with it, but they didn't know what. Then in 1880, a French scientist called Lavaron was looking at these black blobs when one of them suddenly sprouted tentacles and waved at him through his microscope, and he realized they were actually single-celled animals and probably causing the disease. But there was still the question, how did people catch it?
Ross was convinced that the answer lay in mosquitoes, so he set out for India to hunt for malaria parasites. He was unlucky though, because the first place he was able to work was Bangalore, a lovely place in the middle of the south, famous for silk and loaded with mosquitoes like these, but unfortunately they were all culisines. They're vicious biters, but they don't carry human malaria, and he wasn't able to isolate his parasite. Then in 1897, his luck changed. He was moved to Secunderabad, and at Secunderabad, they have different sort of mosquitoes, these ones, Anopheles. Now, he was able to breed 10 of these on the 16th of August, and he persuaded a chap who had malaria to put his hand into a tank, just like this, with these 10 mosquitoes. He paid him the magnificent sum of 1 anna per mosquito, a total of 10 annas, about half a p. Ouch. They've got sharp teeth, these things. And what's more, when they're full of blood, they start pooing it onto my hand to make room for more. I've got at least a dozen mosquitoes feeding on my hand, and I can feel every one of them. He then dissected 2 mosquitoes every day for the next few days to see if he could find the parasites. And on the 4th day, the 20th of August, he actually found them, and he christened it Mosquito Day. Now, while I would love to get my own back on these mosquitoes, dissecting them is fiendishly difficult, so I've recruited the help of an expert, Dr. Phil McCall. Phil, tell me what you're doing.
I'm trying to dissect out the stomach of the mosquito. It was in the stomach wall that he found the large cells where the malaria parasite was developing.
And why was that important?
Because it showed that the malaria parasite was actually depending upon the mosquito in some way, and it was multiplying in the stomach wall of the mosquito as part of its development.
And what was the next stage?
Well, when he continued his work on bird malarias to try and complete the whole cycle, he found that these cells in the stomach wall of the mosquito were actually full of smaller cells, which he called rod-like cells. And these rod-like cells burst from the large cells into the mosquito and eventually made their way forward into the salivary glands of the mosquito.
Okay, so that was the critical moment.
Yeah.
Ross had solved the puzzle. He had tracked the malaria parasite into the mosquito's gut, into its salivary glands, and then back into the victim's blood.
He came back to England and was given a job as a lecturer in this very building. When he heard about the Nobel Prizes, he was so pleased with his malaria work that he wrote to the prize committee and said, "Please, can I have one?" And they wrote back and said, "Certainly not, we'll decide who we're going to give them to." Well, he was actually nominated in the very first year. And in the following year, 1902, he was awarded the Nobel Prize for his fantastic discoveries through the microscope. Which was odd, really, because a few years earlier he'd written, "For the solution of the Indian fever question, they are much mistaken who imagine that so vast a problem will ever be solved by a single coup de microscope." But that was exactly what he did. In 1932, the world of experimental physics was buzzing. The race was on to find a reliable way of splitting the atom. My next hero was a rising star, and he won the race. His crucial breakthrough led to the birth of the nuclear age. He learned his love of technology in this very mill at Todmorden in the Yorkshire Pennines. His name was John Cockcroft.
John Cockcroft was a quiet child who went to school only part-time and spent the other half of the day working in the family weaving business at Burke's Mill. This is the Cockcrofts' home, conveniently just over the road from the mill. Throughout the 19th century, scientists thought that the smallest unit of anything was the atom, and that you couldn't break an atom into smaller bits.
When radioactivity was discovered about the turn of the century, people realized that atoms could fall apart. And a chap called Ernest Rutherford used the radioactive bits to knock other atoms into pieces. But he could only do it with a few atoms, and he had no control over it. And the challenge of reliably splitting atoms was what Cockcroft set out to tackle in 1932. Now, this was the state of play. People knew that an atom was made up of two parts. A hard central nucleus, here it is, I've got two protons, that's my oranges, and two neutrons, that's my apples. And then the protons would be matched by two electrons, these grapes, and the only way you could tell what sort of atom it was by the number of particles. Here I've got two protons balanced by two electrons, and that makes it a helium atom, whereas this, one proton and one electron, is a hydrogen atom. Now, when people talked about splitting the atom, what they meant was actually splitting this hard central nucleus. Burke's Mill used to be a weaving shed. They had a steam engine and a water wheel, and it was here that John Cockcroft, as a lad, got his inspiration. So I thought I'd have to come back here and try and tackle what was then the holy grail of physics, splitting the atom. For his greatest work, Cockcroft teamed up with an Irishman called Ernest Walton, and they tackled the atom-smashing project together. They needed three things. First of all, a projectile. They decided to use protons, that's hydrogen nuclei, and for my hydrogen nucleus I'm using this toy car. Then they needed a linear accelerator, and this is mine. It's in a straight line, so it's linear, and it accelerated the protons by using electric fields. That's what they use. I'm using electric motors. One bit of acceleration there, one bit here, and a third bit here. So it goes faster and faster until it hits the target, which was a lithium atom. A lithium atom has 3 protons and 4 neutrons. Now, the established view was the best chance of smashing the lithium atom was to turn up the voltage to the maximum and give it the highest possible speed. They had nearly 1 million volts to play with. And let's see what happens when I fire my projectile at my target. 1, 2, 3. Ah! It's bounced off. And that's what kept happening to them, time after time. They needed something extra.
Then Cockcroft came across a scientific paper by a Russian physicist called George Gamow, who had dreamed up quantum tunneling. In his paper, Gamow said you shouldn't think of something like a proton as being just a particle. You should think about it at the same time as being a wave. Now that's really bizarre. Things don't behave like this in the real world, but that wasn't the real world, it was the world of quantum physics. Something very peculiar happens if you think this way. First, because the incoming particle is also a wave, you can't say for certain where it is. And stranger still, if you match the wavelength of this incoming particle to the wavelength of the particle in the nucleus, it turns out that 1 in 100 times the incoming particle is already inside the nucleus. Very weird. And Cockcroft realized that if he thought about his protons as being part particles and part waves, then there was a chance of getting through this quantum tunnel as long as they got the wavelength right. And that meant they had to turn down the speed of their projectiles. So now I'm going to run this at lower speed. Low speed. So I've got my wavelength right. And then we'll go 1, 2, 3, there. Slower, it's going slower. I've split the atom! Look at that! From my lithium, I've got 2 atoms of helium. Look, with 2 protons and 2 neutrons. 2 protons and 2 neutrons. And here's the one that we thought of as the wave. And when Cockcroft did it, he was so excited he danced down King's Parade saying, "We've split the atom! We've split the atom!"
With their linear accelerator, Cockcroft and Walton opened the door, the quantum tunnel, to the nuclear age and changed the course of history. For their brilliant work, they were given the 1951 Nobel Prize for Physics. Headingley in Leeds is famous for its cricket ground, but it should also be famous for the fact that just up the road, my next hero invented a brilliant way of separating very similar chemicals. He was a train spotter and a biochemist, and he shared the 1952 Nobel Prize for Chemistry. His name was Richard Synge.
Synge was an absent-minded child who wasn't let out alone in case he got lost. He became a quiet academic with a passion for trains. He would study train timetables and then travel the globe to pursue science and train spotting.
Synge developed the most extraordinary dress sense. He wore a pair of corduroy trousers, which were so low-slung and so loose that they simply didn't hold his shirt in. And at the bottom end, they were so short that they ended miles above his ankles. In 1941, he won a scholarship and came to work at the Wool Industry Research Association base at Torridon. Unfortunately, the only thing that's left now is a little grassy patch and these rather elegant gateposts. Synge's job here was to work out the structure of wool. They already knew that wool is basically made of keratin, which is a protein. It's the same stuff that hair's made of, and fingernails and hooves, if you're a horse, that is. But they didn't know about the fine details of the structure.
And the only method they had to work on was something called chromatography.
The way chromatography works is by using 2 layers, one fixed layer and one moving layer. You put the mixture you want to separate on the fixed layer, and then with luck, the moving layer, as it goes past, will separate out the separate components.
It's dead easy to try at home. All you need are some Smarties, a bit of blotting paper, and some water in a glass. The water soaks up the paper, and the brown dye separates out into its components, red, yellow, and blue dye. Hey presto, chromatography in your kitchen. Synge worked with a chap called Archer Martin, and together they realized that this technique wasn't good enough to separate the components of the keratin in wool, the amino acids. So they had to invent a brand new technique. As a student, Synge no doubt visited the local pubs, and since his lab has been demolished, where better to recreate exactly what he did? The trouble is that molecules are rather hard to see, so I thought I'd try and show you how it worked with some rather larger objects, these bar snacks. I've got some peanuts and some raisins and some sort of crunchy coated peanuts. I've got two layers here. My stationary layer is the bottom one, that's water, and then on top of it I've got a layer of cooking oil. And the water's going to stay still, and the top layer is going to move when I turn on the tap here to let out more cooking oil. And I'm going to take my mixture, and I'm going to sprinkle it in a line across here like this. And then I'll turn on my cooking oil. And they should all start moving. Here it comes. That's great. Now the reason they used two liquids was that they could fine-tune the liquids and choose things that would just separate molecules that were extremely similar.
Now, the running on this course seems rather slow, but both the crunchy ones and the peanuts got off to a good start. In fact, the crunchy ones are already beginning to pull ahead. And you can see why. They're on top of the oil going fastest, while the peanuts are halfway between the oil and the water, making them a little bit slower. But it's a disaster for the raisins. They've sunk to the bottom of the water right back at the starting line. The first over the finishing line, the fastest, our winners, the crunchy coated peanuts.
So there we are. Look, all the crunchy ones are on the finishing line. The peanuts are in a neat group here, and the raisins hardly moved at all. We've achieved complete separation. And that's how Martin and Singe achieved complete separation of a very complicated mixture of amino acids by using subtle combinations of two different liquids. I've separated with my machine raisins and peanuts and these crunchy coated peanuts. Now, have you got some dry roasted and some ready salted? Thanks very much. What I'd like you to do is build your own machine and see if you can separate different sorts of peanuts, like salted and dry roasted. And if you can, take a video of it or a photograph and write to me details of where to write at the end of the programme. At the end of the series, we'll put the best results on the telly. Good luck.
My next hero was the first person to look inside a complicated organic molecule, penicillin. It sounds easy, but the penicillin molecule is so minute you couldn't possibly see one under a microscope. And the atoms inside it are smaller still. And yet, she worked out not just the structure, but the exact position of every atom in the molecule. Her name was Dorothy Hodgkin.
Dorothy Hodgkin was born in Cairo, but aged 4, her parents sent her to live in England. At the age of 10, she became really interested in chemistry. She was so keen she set up her own lab in the attic. It stood her in good stead as she ended up at Oxford.
Dorothy Hodgkin came here to Somerville in 1928. It was then an all-women's college. She was studying chemistry, and that made her very unusual because in the whole university there were only 3 female science students.
Of all the things she studied, she got most excited by a newfangled technique called X-ray crystallography. This technique had been invented by Nobel Prize winners William and Lawrence Bragg. They found that when you fire X-rays at a really simple crystal, the X-rays are bent or diffracted, and patterns appear that tell you exactly where all the atoms are inside the crystal.
The Braggs did all their work on crystals of salts, things like sodium chloride, which is ordinary table salt. And here is my sodium chloride, and you'll see this is sodium, chlorine, sodium, and so on. You'll see that although the crystal has thousands and thousands of atoms in it, the structure is very simple because it does simply go sodium, chlorine, sodium in every direction.
Dorothy Hodgkin wondered whether she could use the same technique to probe the secrets of the much more irregular molecules found in living things.
To work out the structure of something, you need a crystal. Suppose that this is the molecule I'm interested in. I can't work on just one molecule, it's much too small. What I need is a whole crystal, thousands of molecules all lined up together. Now, if I'm lucky, I can get this one to join up with a whole lot more like this to form a great sheet with rows and rows of these molecules in all directions, and then several of these sheets to join up together like this to make an enormous three-dimensional structure with thousands of my molecules all arranged in lovely straight lines. The next thing we need
is some X-rays to shoot through the crystal. Instead of X-rays, I'm going to use caster sugar because it's cheaper and it's easier to see. And I'm going to zoom it through here like this, just sprinkling it on. Well, actually, I'm casting it on because it's caster sugar. And you can see that the sugar would fall straight to Earth if there wasn't any crystal there, but because there's a crystal, it will have been diffracted. And if I lift up the crystal carefully now, we'll find that it's left the sugar in rather a curious pattern with a lot of lumps and holes in it. If I do the same thing with a different crystal made of different molecules, you can see they're different shapes, same sort of X-rays here. Again, they're being diffracted, but they're diffracted differently because of the different shapes of the molecules. Let's have a look at this. And you get an entirely different sort of pattern. You see there's quite a lot of hills around there, round a sort of circular hole in the middle, whereas this, you can see that it's quite distinct. Clearly, there's a connection between the pattern you get by diffraction and the structure of the molecules in the crystal. It's not as though you get a photograph of the molecule, but there must be a connection, and in fact it's a mathematical connection which had been worked out 200 years earlier by a Frenchman called Jean-Baptiste Fourier, and the process is known as a Fourier transformation.
In 1942, Hodgkin started to work on the structure of the antibiotic penicillin that had been discovered 14 years earlier. The X-ray diffraction pattern she got from penicillin was the most complicated that anyone had ever tried to work on, and it took her and her colleagues 2 years to do all the mathematics.
This is an exact replica of the model she made to display her penicillin molecule. If you look in here, you can see some of the atoms between the layers of perspex, and scattered through the rest of this three-dimensional object are all the other big atoms showing exactly where they were. If you join up the atoms with bonds, this is what you get. This is the shape of the penicillin molecule. It's not like that, it's not like this, it's like this, because that's what her X-rays showed her. And armed with this knowledge, the chemists were able to use the same sort of structure in new molecules and make entirely new antibiotics.
But she didn't stop there. In her lab in the Natural History Museum at Oxford, on the middle floor up there, she went on to tackle vitamin B12. Cracking that took her 8 years. But her greatest achievement was yet to come. In 1966, she worked out the structure of the hormone insulin, a task that took her 34 years and ultimately led to new treatments for diabetes. Dorothy Hodgkin was a brilliant scientist. She turned crystallography into one of the most useful techniques in the chemist's toolkit, and she was the first British woman to win a Nobel Prize. I'm sorry, that's all the Nobel heroes. See you next time. If you want to send me pictures or video of your peanut separator, write to Local Heroes, PO Box 267, Leeds, LS7 2BE, or look at my website for more details at www.bbc.co.uk/history.
All the right moves in the property market. Next tonight on BBC Two, Quentin Wilson with the last in the series. The step-by-step guide to the best of Adam Hart Davis's experiments are recreated in this BBC book.